So just a reminder, this is sadly enough our last week. So last class is Thursday. Where the final will be posted tomorrow. And due Friday at 11:59 p.m. As I said with the other exams, you guys know I'm very lenient. If you have a logistic issue, if you have any issues with completing the test in this time frame, just reach out to me. We'll take care of you. The purpose is to learn. The purpose is to acquire skills. That's what we want. So please let me know if that doesn't give you the appropriate time to get things done. We will have class Thursday because we will want to talk about things and you'll likely have questions. So it makes sense to do that. So I hope that everybody's okay with that. Okay, good. So you guys are stressed out because there's no doubt you are, because everybody gets stressed out with what's happening here when we gave you that last homework, homework 7. That is a scary looking creature because it has all kinds of series on there. And not only that, but they, aesthetically, for someone at your experience level and in your level of exposure to higher mathematics, is undoubtedly looks scary as, HE double hockey sticks. Can we say hell? Yeah, we say hell, even though we're recording this on the YouTube machine. Although that brings me to, before we get back to this, I noticed two things that was brought to my attention in the other courses, and I need you to point this out. I was grading your exams and putting sort of comments on there, but some students are saying they don't see any annotation on their graded exams. So you guys got to let me know, because if you should be able to see the stuff that I put on there, so that you can hopefully learn from it. So please let me know if you're not seeing, like, yeah, see, that's interesting, Paul. You said you can't, and no one's complained about this yet. And the other thing that I noticed someone complained about is you guys said you can't find the lectures, but when you log on to Canvas, you should see the YouTube embedded videos of all our lectures, and there's also a link. Oh, you have to download it, Matt. Okay, so Matt says you got to download it, and then you can see. Okay, yeah, I don't know. I'm learning. Look. I'm this online stuff. It happened so fast. I didn't really get a chance to prepare all that kind of stuff that you're just not used to doing. So we're sort of all learning together. I hope we understand that. And I hope you don't get too mad at me. Although I guess you can get as, mad as you want. I won't know. You might be sitting there with your black screen right now, flipping me off. I have no idea. Cursing me under your breath. So please, if you have any questions about your exam grades and how I was grading them, please reach out. The homeworks, I grade a little different than exams. I don't grade every problem. It's sort of like a lottery, which problems get graded. And so please let me know if you have concerns. Your grades need to be submitted by Monday. So there's still time for us to remedy any fears we might have. Okay. So where are we at with the big picture here? The big picture is we're currently studying series. Particularly, we always just say series, but they're really, the correct name is really infinite series. So let's, and sort of put this into sort of how we've structured it, is the goal, ideally, what we want to know, does some series converge? So, and then if so, to what? So let me go back. So remember the big problem here. The pie in the sky is, does a series converge? And then if it does converge, the next thing, which we pointed out is not always possible, but the next thing in an ideal world is if it converges, what is its limit? What is its sum? So what we found is for geometric series, we can do both. So what does that mean? That means if, and again, we keep writing this, and if this number r is between -1 and 1, then the geometric series r, k goes from, say, 0 to infinity, is 1 over 1 minus r. So not only does it converge, but we can tell you what the limit is. The limit is 1 divided by 1 minus whatever that number r is. So on homework 6, and also we repeated the problem, some of them on homework 7, geometric series, not only does it converge, but we could tell you what the limit is. And of course, if the absolute value of r is greater than or equal to 1, then this guy diverges. And so, in general, though, the best we can do is apply a yes-no test. And so these are called convergence tests. So we did 2 of them on last Thursday. So we studied 2 already. So what were the 2 we've covered so far? The first was the divergence test, which you should know how to apply it. And then the second was the so-called integral test. So you got to think of these as you have a toolbox, and a mechanic or a contractor might have hammers and nails and all kinds of different screws and different tools, tape measures, and all kinds of other things. Or if I am an auto mechanic, I have tools for working on the cars. If I own a salon and I do hair, I have different tools for cutting hair and making hair look nice. If I'm a doctor, I have certain tools. Well, in the science, math, and engineering world, these are our tools. This is our toolbox, these tests. And so you got to practice and you got to have experience to know what test to apply when. And so what we'll do now is talk about some more tests. So today we start with the comparison test. So its name, excuse me, it is very self-explanatory. So let's motivate it in the following way. So assume I have 2 series. So assume that 0 is always less than or equal to a sub k, and a sub k is always less than or equal to b sub k for each k. So imagine I have two lists of numbers. I'll call the first list A1, A2, A3, A4, blah, 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 blah. I'll call the next list or the next sequence B1, B2, B3, B, blah, blah, blah. Now, let's also assume that if you match up the corresponding entries, the first term, B1 is always bigger than B2. B1 is always bigger than A1. B2 is always bigger than A2. B3 is always bigger than A3, etc. And on top of that, let's also assume that the BK converges. Well, okay, what can we say? Well, what can we say about the series where we add up the A's? Well, let's just appeal to the definition. Let's not even get cute. Let's go right to the definition. So pick any n, in particular, any positive integer. What we can say is 0 is clearly less than or equal to a sub 1 plus a sub 2 plus a sub 3 plus all the way up to a sub n. But we also assumed that each one of these a's was less than their corresponding b's. So we can reason that the sum of a's can be no bigger than the sum of b's. But this can be no bigger than this if we add them all up. So if we just add up n of them, that has to be smaller than we add up all of them. But we assumed that the BKs converged. So this equals some number. We'll call it L. So again, think about, you know, think about what's happening here. We're telling you that this number, no matter what n is, if you add up all the a's, they can be no bigger than when you add up all the b's. So the only conclusion is thus S sub n, which is just the sum of the first n terms of A, this guy is a bounded increasing sequence. And it must converge. I highly encourage you to really ponder the logic here. So what we do is we summarize as a theorem. And so this is called the comparison test. Let A sub k and B sub k be series with positive terms. So we want to study two scenarios that can be deduced from the previous page. So two scenarios. If the A sub k's are always less than the B sub k's, and the B sub k's, if you add them up, if that series converges, then the series of the A sub k's converges. And then, of course, if you reason in the opposite direction, if the B sub k's are less than the A sub k's, and the B sub k's diverge, then we have to reason that the A sub k, the series as we sum A from k equals 1 to infinity, diverges. Okay, so this is an awesome and it's powerful, but the problem is it's only useful if you have something to compare it with. So let's think about that. Before we move to the next page, does anybody have a question? So if we want to use this test, if it's going to be of any use to us, we need to have, if we have an unknown series, if we want to compare it to something, we have to have something that we already know how it behaves. So for example, we have the geometric series, that's good. So we already have that. So another important class are the so-called P series. So suppose we have the following. So this is going to look like a geometric series, but it's not. The series 1 over k raised to the power p. So k is the index. So let's say 1 to infinity. So what does this look like? Well, this is 1 plus 1 over k, excuse me, it's 1 over k, losing my mind. Writing it all down wrong, losing my mind. So p is a fixed number. So what is k? When k is 1, you have 1. When k is 2, you have 1 over 2 to the power p. When k is 3, you have 1 over the power 3 to the power p. This guy converges for p greater than 1 and diverges for p less than or equal to 1. And this is a very easy argument to do it. This is based off of the so-called integral test. So let me reiterate this again. It converges for p bigger than 1, but it diverges for p less than or equal to 1. And so the way you can verify this is you can use the integral test. Instead of doing that, though, let's just look at a couple examples to illustrate this. So this guy, 1 over k squared, k goes from 1 to infinity, converges. Why does it converge? It converges because it's a p series. And we can even tell you what the p value is. It's p equal 2. However, this creature, 1 over k, diverges because it too, it is a p series. But this time, p is 1/2 because the square root is the 1/2 power. All right, so let's see how we can use these when we're studying and when we want to do a comparison test. Yep, hold on, Michelle. Does anybody have a question, by the way? Cool. I just realized I was making faces at the camera as if you guys aren't looking at me. Like I'm all by myself. I'm like, you guys are probably, what is wrong with this dude? So here's a very typical example of how we can use the comparison test. So let's take something like 1 over k squared plus 5. K goes from 1 to infinity. And let's just, for practice, write out the first few terms. The first term is 1/6. The second term is 1/9. The third term is 1/4. What is it? So when I plug in 3, I get 9 plus 5 is 14, etc. Does this guy converge? or diverge. So here's the way I would encourage you to think about this. So the term 1 over k squared plus 5 suggests. Now, why does it suggest? Well, I have experience. It's not going to suggest it to you because you don't have experience. That's why we ask you to practice over and over again. That's why there's hundreds of problems at the end of each section, because that's the only way that humans have figured out how to learn math and science, by doing it. Just like the only way you're going to learn how to play basketball is by doing it. Just like the only way you're going to learn how to play baseball is by playing friggin' baseball. You ain't learning this through osmosis. You ain't learning it by listening to me or some other jolly fool on YouTube. The only way you're learning this is by getting out an instrument that writes and paper. That's it. I wish it weren't that way, but that's the way it is. So this term suggests comparison with 1 over k squared. Now, you got something for everything, Paul. I like that. I like that, Paul. At least I know you guys are awake. So my experience tells me that I should compare this with this because, why? Because as we showed on the previous page, 1 over k squared is a convergent p-series. So how do we apply the comparison test? Well, here's how we write it. So since 1 over k squared, did I do plus 5? Is that what it was? Yeah, plus 5. Since 1 over k squared plus 5 is less than or equal 1 over k squared when k is bigger than 1, we conclude by the comparison test that this guy converges. So here's what I would encourage you to do is right now, and then these are some of the ones that you guys asked about. So this idea works on the following guys from your homework. So it's going to work on O, P, Q. If you want, it'll work on R. And I believe that's it, yeah. Does anybody have a question about this particular example? Does anybody have a question or a comment about this? Let's look at another one. So let's try, does 1 over, how about 7k plus pi? So does this converge or diverge? So very similarly, what I would like to do is note the following. I would note that 1 over 7k plus pi is less than 1 over 7k, which of course is 1/7 to the power k. So thus, since this series is a convergent geometric series, we conclude by comparison that this guy converges. So again, this is a little higher level reasoning than you're used to doing. We're not just moving symbols around, we're reasoning, we're using logical deductions. And so this makes it a little harder to learn. It takes lots of practice to get good with this stuff. Does anybody have a question? All right, now, before we leave today, I'm going to give you hints for all these homework ones, every one of them, so don't stress about it yet. But they're very much all the same in flavor once you realize, again, I know that's it's easy for me to say they're the same, being the expert while you guys aren't, but you'll get there. I promise you. All right, so our next test works for series where the sign alternates. Such as something like this. So here's a series that looks kind of scary. When k is 1, you get 1, then it's minus a half, plus a third, minus a fourth, plus a fifth. So notice the idea is that the sign alternates. So this is called, creatively enough, the alternating series test. So if I have terms that alternate sign, how do I get them to alternate sign? I put this -1 to the k plus 1. So this guy converges if two things are happening. The first is the series, or excuse me, the terms are decreasing. So they're getting smaller. And not only are they getting smaller, they are going to 0. So if you think about the divergence test says that the condition 2 isn't enough. But now we're saying if we impose a second condition, that is the terms are going to 0, but they also alternate, then we will converge. And there is a slight technicality here. This is for all terms greater than some fixed number. So basically what that means is we don't need this to happen in the beginning of the series, but way out at the end, they have to be going decreasing. So they can bounce around in the beginning, who cares? What we're wondering is at the end, they have to be going down. And that's really just a technicality. That's not going to come into play with us in calculus class. So there's a very cool consequence about this, though, and the best way for me to get you to think about this is this important theorem. And so the theorem says, this is about our old friend, the harmonic series. Recall, this guy, 1 over k, which is 1 plus a half plus a third plus a fourth, this guy diverges. But if we make it alternate, it converges. So what this theorem tells us is it says, okay, this is a good example. We know the proof of this is straight, well, so the proof relies on the divergence test, integral test, and alternating series test. So, I'm being kind of vague there, but I'd like you, if you want to learn this, this is what you got to do. You got to get what we say, your hands dirty. You have to think about these statements and write these things out, and then go to calculators and compute partial sums, and then think about the logic behind these theorems, these alternating series tests, and the integral test. That's how you learn this. You don't learn it by memorizing examples. But what this theorem suggests is there's actually something deeper happening. that there's something else that's really important at play in the background. And so it's going to suggest we make a definition. And by the way, before I make this definition, does anybody have a question? I mean, we're throwing a lot at you, but such is life. Any comments, questions? We good? All right, so let's think about what we have here. So the previous theorem suggests we classify special properties. Now, once again, I know it doesn't suggest it to you. You are the amateur. But what you want to do is you'd like to get to a point of understanding where you're like, okay, I see why O'Grady wrote this or why he said this. So let's make a definition. Let's take a series, but instead of looking at its numbers directly, let's say, what if we take the absolute value of each term, and let's assume this converges. So if the absolute values converge, what we say is we say the original series without absolute values converges absolutely. So that's the new term. We're adding sort of like this adjective, or so you could think of it as like absolute convergence. It's a stronger notion of convergence. And so there's a subtle distinction we can make, and that is if the absolute values of the terms diverge, but the regular series converges, we say the convergence is conditional. So it turns out in many important applications and theoretical things that we want to do that distinguishing these two properties is very important. So there's like a hierarchy here. So what we're doing, when I say classify, let's look at a picture and maybe it'll make a little more sort of sense. If we have series, so let's even write down what it looks like. Let's remind you, it looks something like this. There are two options with this thing. Option one is it can diverge. Option 2 is it can converge. And then not only can it converge, it can be absolute or it can be conditional. So we're classifying these things because it turns out in applications it's very important. It's nice to be able to classify things. We do this with everything. Short, tall. Online learning, face-to-face learning. Can, energy drink. Water. Water, not the same as energy drink. We distinguish things. That's what we're doing here. Regular pen, Bluetooth pen that writes on computer tablet. We distinguish between the two. That's what we're doing here. I guess I should spell hierarchy correct. No one yelled at me about that. You guys got to learn to correct my poor grammar. Hierarchy. Hierarchy. Okay, very good. Very, very important as well. So since we don't want to waste too much space, so we'll put this here. We'll go, woo. So we have 2 more tests. And we save the best for last, at least for application purposes. Maybe. The first one is called the ratio test, and the second is called the root test. So we know in order to converge that the terms have to be getting small. But we know that's not enough for them to get small because the harmonic series, the terms are going to 0, but we showed it diverges. And so we know there's this subtlety at play. And so what that tells us is if we can somehow quantify sort of, and this sounds silly, but the speed at which your terms are going to 0, how are they approaching 0? Are they going quickly to 0? Or are they slowly going to 0? And if they're going too slow, is that enough? And so what we can do is we can say if there's some sort of particular behavior we can exploit, then we should do it. And so the ratio test and the root test do just that. So let's just sort of spit them out. If you study limits and sequences, you know, in depth, if you play games, you do numerical investigations, you'll notice there's certain themes and there's certain patterns that you can exploit. Now, some student in calculus 1 and 2, you usually don't have enough experience to notice that, but it is there if you investigate enough. And so what happens sometimes is we have to just give you information, and it doesn't seem that it comes from any intuitive place, or that it comes, you know, you might say, well, how would I ever think of this, or who thought of this? Well, don't forget, calculus was developed by a lot of really smart people over a long time. So even though when we state some of these things, they might seem like they're completely out of the middle of nowhere, they're not. It's just that if we wanted to motivate every topic from an intuitive standpoint and and sort of teach it in a way that is intuitive to you, I mean, we would never get anywhere because it takes forever to do that. So we have to pick and choose when we do that. Now we do that for some things like the integral and the derivative. We try to give you sort of intuitive motivation, you know, areas and tangents. But with some things, it just seems completely out of nowhere, and you just got to deal with it sometimes. And for many students, this is the case with the ratio test. But I will tell you, think about this as a way of measuring how the terms are getting small for a convergent series. So here's the ratio test. So let's consider this guy, some arbitrary series, and compute the following. We'll call it L equals to the limit as k goes to infinity of the absolute value of a sub k plus 1 over a sub k. So we're going to compute a limit. So we know with this limit, there's a scenario. It can exist, it can be a number, or it can not exist. That limit might not exist, and we'd say it's infinity. So there's three things we're going to break it down to. One, if, excuse me, if L is less than 1, the series converges. And it doesn't just converge, it actually converges absolutely. And then, of course, number 2, if L is greater than 1 or in infinity, the series diverges. And then the last scenario is if L equals 1, the test is inclusive. Or not inclusive, inconclusive. Okay, so does anybody have a question about how this is stated or comments? Okay, so let's see how you use it. So let's compute or test this guy. So let's say we have 3 to the k over k factorial. So some of you might not remember what factorial means. You might need to review that. Let's write out the first term. This is 3 plus 9 over 2 plus 27 over 6. 3 to the 4th is 81. 4 factorial is 24. Turns out, though, this guy does converge. So let's see why. So the first thing we're going to do is we're going to compute the limit as k goes to infinity of the kth plus 1 term over the kth term. Now, the first thing to notice in this particular problem is everything's positive, so the absolute values are redundant. This is 3 raised to the k plus 1 over k plus 1 factorial, all over 3 to the power k over k factorial. So this looks like a big ugly thing, and it is, but turns out everything, not everything, but lots of these things are going to simplify and cancel away. Clean this up real quick. This is so it might be useful to remember how the factorial behaves, and some of you might say, I don't ever remember a factorial. Well, what is k factorial? K factorial by definition is k times the previous number times the, maybe I'll write this like this. So you might need, if you got to Google it, you got to Google it. This reads k factorial. So what does k factorial mean? Well, in general, 1 factorial is 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And so if this pattern continues, what is k factorial? It's k times k minus 1, all the way down to 2 times 1. So some of you may have been exposed to the factorial before. It's just a shortcut. It's a shortcut notation. Okay, so let's look at this. And it's also useful, on the next page we're going to write it down. Let's go back to our purple. So we have a big fraction, and one of the things we learned as children that we often forget is if you have a fraction divided by another fraction, you can multiply by the reciprocal. So this is really 3 to the k plus 1 over k plus 1 factorial times k factorial over 3 to the k. Now, it's useful before we do the next step to think about how the factorial plays when it's in this form. So let's take something like 5 factorial and divide it by the 6 factorial. So by definition, this is 5 times 4 times 3 times 2 times 1. Well, this is 6 times 5 times 4 times 3 times 2 times 1. And if you cancel all the common factors, everything in the numerator goes away, and only one number survives downstairs. And so this is 1 over 6. So if you apply this argument in general, what you learn is k factorial divided by k plus 1 factorial simplifies to just 1 divided by k plus 1. So you should convince yourself that that's true. And so what that means then is lots of things up here in this purple are going to simplify. For example, what's going to happen? Well, this 3 sub k cancels with this 3 power k. And so the only thing that's going to survive is 3 over k plus 1. That's it. And this guy is clearly 0. And that's a limit from way back in Calc 1. Okay, so here's what we know. The following is true. Since L, which is this limit, since it's equal to 0, and that's clearly less than 1, the ratio test guarantees convergence. So we know the series, the original series, converges. Does anybody have a question or a comment on this example? One of the things that if you practice, you'll learn very quickly is anytime you see a factorial, think ratio test. You see a factorial, think ratio test. Any comments or questions? All right, so the last test is the ratio test, excuse me, the root test. And it is nearly identical to the ratio test. So for this guy, there is only one difference. The only difference is we set L, instead of using a ratio, we use a root. So we set L to this limit. We take the limit of the terms, we take their absolute value, then we take the limit of their kth root. So it turns out in practice, in most applications, the most useful, I'm going to say most useful, but the one that shows up in, especially in what we're going to be doing moving forward, is the ratio test. Although the root test is also useful as well, but you know, in my opinion, it doesn't come into play as quite often as the ratio test does. So the big question that everybody always asks Luckily, the book talks about this. And you're going to say, how do I know which test to use? And the answer you don't want to hear: experience and practice. That's it. There's no easy answer to this. It's experience. And doing this is a skill. Just like if we all said we're going to have the O'Grady 5K tomorrow, and I said we're all going to meet outside and go run 3.12 miles, I guarantee you we would all finish at different times. And if we had a push-up contest, we would all be able to do a different amount of push-ups. And if we were playing baseball or softball or basketball, or we were seeing who can play the piano or who can play the trumpet, every one of us has a different skill level at all those things. If I wanted to learn the piano, it would probably be terrible for me because I've never practiced it before. It would take me a hell of a long time to learn the piano. But that's okay. I accept that if I want to learn the piano, it's a challenge and it requires practice. I am no gifted pianist. Most human beings have to understand that that's how we learn math and science. There are very few humans on this planet that just understand organic chemistry when they read it one time. There are very few humans on this planet that understand this by reading it or watching me talk about it. Most of us, myself included, have to suffer to learn this. And when I say suffer, I use that in a good way because it's fun to learn. The struggle is real. Okay, does anybody have a question or a comment about this before we go back to the homework problems? Okay, so let's look at homework hints. So I often find, I don't want to steal all the thunder from you, but what I do want to do is I want you to be able to do this. So perhaps the best thing we can do is tell you how to do them, but you got to fill in the details. And some of them will give you more hints than others. We'll see. So let's just go down. The A is geometric. B is also geometric. You should convince yourself whether they converge or diverge. C, geometric. D is also geometric. Now, I'm not saying you can't use other tests, but if it's geometric, why use another test? Because if it's geometric and it converges, you know what the sum is. So that's the best case scenario, is you have a geometric series. So I'm going to do it like it was done on the page. So then we'll go over here to E. E is a P series. I'm sorry, no, it's not. What am I saying? Losing my mind. E is not a P series. If I said that earlier, I'm wrong. E is geometric. F is geometric. Now, let me give you a little hint on F because it's not so obvious. What you need to recognize is when you were younger, you learned exponent properties. So this is the same thing as 4 over 5 to the minus 1 times 2/5 raised to the nth power. So you have to rewrite this. Another way of writing this is 20 times 2/5 to the power n. Convince yourself of that. For G, try the root test. For H, I would probably try right away. I would probably try the integral test. Does anybody have any questions on A through H before we move down? I know. Yeah, so the questions, Michelle, you asked about were all downstairs. Okay. All right, so let's look at the other ones. For I, what I would do for I is I would try the ratio test. That index in the power makes me think ratio test. For J, this is just a P series. P series, or if you recognize a P series, it's just a one-liner. You don't even have to do any work. So for J, for example, you can use the integral test, but that's an awful lot of work when you know it's a P series. You know, using the integral test when you don't have to is like dropping an atomic bomb on an ant farm. It's completely unnecessary. So I mean, I hope that makes sense. If it doesn't, please speak up. But I mean, that's a P series. It converges. Why? Because its P is 1.001, which is bigger than 1. For K, I would use the ratio test. Now, L stinks. L's kind of a pain. L, you have to suffer. This is the integral test. Although maybe you could probably maybe use the ratio test, actually. I'm not sure. I didn't think about that. But you could definitely use the integral test. You could try the ratio, though. M. That factorial tells me ratio. N, the power there. The only way I can think about handling N is to use the root. But maybe you can find a more creative way. And then for P, I would compare. And I'll even give you another hint. I would compare with 1 over K to the power 3/2. That's a P series. Q's a little more challenging, but I would use comparison. R, you can use alternating series. Or if you wanted, comparison. S looks scary, but that factorial screams ratio. And then last but not least, T, that is a gimme. It's a freebie. This is a P series. So these are all good hints. What I would encourage you to do is you try to do them on your own. And if you're still stuck, shoot me an email or ask on Thursday. Does anybody have a question about any of these while we're still here?
So it doesn't have to be the one on the homework, but could we just work an example using the root test?
Sure, yeah. Like I said, I mean, the root test is one that, you know, it doesn't come up as often in practice as it does in, say, theoretical things. Nonetheless, let's do an example to sort of ease your mind. Anytime you have something ugly raised to the power of the index, that's usually a telltale sign for the root test, but not always. So, you know, I hasten to say, here's the problem with the root test before we do an example, is, as you know, taking limits with the roots is sometimes, we spent some time yapping about that, I believe, was it last class? when we did the sequence and we talked about like L'Hopital's rule and some of those more complicated limits, oftentimes the limit sort of is more complicated when you're employing the root test. But that doesn't mean that you shouldn't know it. So let's look at an example of pretty much of a typical common type of example. So let's look at something like this. Let's say we want to study, how about 3 to the power k over, say, k to the 5th. So suppose you don't want to try, I mean, look, let's also think about this too. Look at this example and think about the sort of the test that you have. You have to start using common sense. I mean, this is nothing that you would try to integrate. Like, you don't want to integrate 3 to the power x over x to the 5th. That's almost ridiculous. So the integral test is completely non-existent here. We don't have anything alternating. So when you come down to it, really, you can maybe try the comparison test. But usually, when you see something that's sort of this, you know, without, if something doesn't look easy to integrate, for example, or if it doesn't look remotely geometric, often your first thing to do is to try the ratio or the root test. So let's look at this guy. So let's ask, does this converge? So let's look at the limit of the kth root of the, we don't need absolute values because they're positive, so this is 3 to the k over k to the 5th, all inside this radical. Now the beauty is the kth power upstairs is going to go to the war, so this simplifies. This just becomes 3 divided by, look at your powers of k, so this becomes the kth root of k to the 5th. Now let's rewrite this in a little more easier to ponder notation. Instead of me writing this as the kth root, I'm going to write this as k raised to the power 5 over k. I'm going to use exponential notation. Now, one of the things that makes the root test hard to use, is that limit. Notice the numerator's fixed, right? But downstairs, what is that going to? Well, the 5 is, we can ignore the 5. Really, all we're worried about is the kth root of the number k. So think about what that limit does. You know, ask yourself, what happens when k is large? Like, what's the 100th root of 100? What's the 1000th root of 1000? Now, that might not be obvious at all to you, but if you looked at that function and graphed it, and you started playing some games, it turns out that this thing is just equal to 3 over 1 to the 5th, which is just 3. And so what we get is we get divergence. Since 3 is greater than 1, root test says divergence. Now, the subtlety here is, how did I compute that limit? So perhaps we can come up here. We're out of space because they only give us 20 boards. But if we come up here and we seclude this off, we can squeeze in the argument. Basically, what I'm telling you, and you should verify this for yourself, is that the limit is k goes to infinity of k to the 1 over k is equal to 1. This is not an obvious limit, so you have to use k to the 1 over k equals e to the log k 1 over k, which equals e to the 1 over k log k. And to verify this, and then you have to use L'Hopital's rule. I mean, that is a complicated integral. But you should work through the details to convince yourself that thing's indeed one. Does this make any sense?
Yes, thank you.
Now, coincidentally, if you use the root test on n, look at n. Well, when you use the root test on n, the kth root is going to kill the kth power, and that limit's much easier than this one. Any other questions, comments, concerns? Paul, why have you paying attention? What was your concern with the Pearson problem?
It was,
I mean, it is separable and you can solve it. Were you having trouble getting the answer the computer wanted?
yes.
Okay, yeah. All right, well, then I'll look at it for you and we'll see if your answer matched mine. All right?
Okay.
Cool. Any other questions from the peanut gallery, all my friends in pleasant peasant land, as I like to say? We had a lot of good culture today. We talked about being pianist. That's a fancy word. You don't just play the piano, you're a pianist.
I think there was a whole Animaniacs joke about that.
Is there really? There you go. All right, so look, there's a lot to learn, and we're out of lots of, we don't have, as the semester's ending. So I really encourage you guys. I don't want you. You do whatever you want. You're all living, breathing humans. But I would encourage you to really work on these and ask questions. Shoot me emails. Blow up my email for the next couple days if you have questions. Don't be afraid. It's not going to make me mad. I'm not going to ruin your final score because you emailed me too much. And then I want you to work on these and ask questions, because we're going to be talking about, so we spent this time with these series now. What does it give us in other aspects of calculus? How does this stuff relate to derivatives and integrals? How can we use these new ideas to learn new things? And that's what we're going to talk about on Thursday, and that's going to be it. So I need you, well, first off, it stinks that that's how it works in the summer, but that's how it works. We take a final right as the class ends. So your final will be due Friday at 11:59, just because I have to grade them, but I will allow homework to be accepted up until Sunday night. So you will have one more homework assignment, and, I know there's a lot, but, just think of homeworks as ways to puff your grade up. All right, any other questions, comments? Well, listen, I appreciate it. I thank you guys for joining me. Hopefully it was a learning experience and you're not too stressed. And best of luck, and I will talk to you Thursday. Thanks again. Take care.